So my topic is recent developments in cosmology. Particularly, I want to talk about the so-called Hubble tension. Actually, this is a very hot topic in recent history of cosmology. I just have an overview of what this term means, Hubble tension. So my talk will be mainly on the observational part of cosmology. And we have to start with the modern cosmology when it began. It is almost only 100 years that the spiral galaxy in the Andromeda constellation was identified to be outside our Milky Way galaxy. Actually, people thought, until that time, people thought that the Andromeda galaxy, that name was, it was considered to be a nebula, not another galaxy. Actually, our galaxy is relatively small when compared to the distance between galaxies. It is only some 15 kiloparsec. One parsec is some 3.26 light years. So 15 kiloparsec means some 50,000 light years. Our galaxy is only of that much radius. But the Andromeda galaxy was initially thought to be a nebula there. But later, it was the scientist Opik who first measured the distance to the Andromeda, and there onwards people called it the Andromeda galaxy. Its scientific name is M31. He measured it to be some 451 kiloparsec. So it was the first time when people realized that our universe is something outside our Milky Way galaxy. It's so vast. See, actually this is the nearest galaxy. Andromeda galaxy is the nearest galaxy to us. And now we understand that our universe extends to such a large distance, some 3000 megaparsec. We can see objects up to that distance. So by the discovery of Opik, we can say that the modern cosmology started. And the famous astronomer Edwin Hubble measured the same distance, but his value was 285 kiloparsec. That is slightly less than that of Opik. And the modern value, the recent value as we know it now, its value is 740 kiloparsec, and that is some 2.5 million light years. So the Andromeda galaxy is at such a large distance. 2.5 billion light years means some 25 lakh light years. So when you observe that galaxy now, the light from it started from there some 25 lakh years ago. And we are seeing it as it existed at that time, not as it exists now. So that is a very important point we should keep in mind. The measurement of distance, that is what I wanted to introduce first. So another thing which we in cosmology are interested in is, see, actually we have to understand what is the Hubble's discovery. I think most of you know it, but I just for the sake of completion, I am just mentioning it. The measurement of spectrum of these objects, study of the spectrum, and I hope you know what is meant by blue shift and red shift. So in Hubble, 1929, Hubble observed that there can be a certain law like this, and that law says that I explained C is this H0D. C is the speed of light, and Z is the quantity which we just mentioned, the redshift. And D is the luminosity distance to a galaxy. So this is a proportionality relation between Z and D. And H0 is a proportionality constant, and that is what we call the Hubble constant. So the measurement of Hubble constant is very important in explaining the expanding universe, the concept of an expanding universe. So what is the importance of H naught I will tell you. Initially Hubble estimated that value to be 535 kilometer per second per megaparsec. That is unit of the Hubble constant, kilometer per second per megaparsec. Hubble estimated its value to be 535, and that was a huge value. Why I say that is a huge value is this. If we consider a universe which is expanding uniformly, if the expansion is uniform, then the reciprocal of H naught will be approximately the age of the universe. So H naught raised to minus 1. H naught raised to minus 1 is the age of the universe, if the universe is expanding uniformly. So if the value of H naught is around 500 km per second per megaparsec, in that case, the universe should be approximately of the age 2 gigayears, 2 billion years. This will lead to a contradiction. The contradiction is that when radioactive material, say for example geological rocks, etc., when they are studied, the age can be determined using radioactive dating techniques. And what we see is that such rocks are found which are 2 to 3 billion years. So how can the universe be of a lesser age than that? Even on Earth we find objects which are more than 2 billion years old. So that is what we call an age problem. So the measurement of H naught is closely related. In several times in the history of cosmology in this 100 years, such age problems appear. So that is all related to the value of the measurement of the value of H naught. So Hubble observed it to be, obtained it to be nearly 500 or greater than 500 units, kilometer per second per megaparsec. But that remained a problem until then, 1950, when three astronomers measured its value to be 180 km per second per megaparsec. So that is a lesser value, and the astronomer Sandage once again made a measurement, and he obtained it to be between 50 to 100. So that value is reasonably good, because that is a relief from the age problem. So the measurement of H naught all through these 100 years is still vague, in the sense that we are not able to precisely make the measurement or estimate the value of H naught. So this 50 to 100 km per second per megaparsec was a somewhat reasonable value, but people tried to measure it exactly, and that attempt is still going on. I'm just giving an overview of all these. See, if we consider cosmological models, I think Shivkumar will be introducing the various cosmological models in the afternoon. So if you consider a simple cosmological model which is nearly empty, in that case H naught equal to 50 km per second per megaparsec will have an age of 19.3 gigayears, 1 gigayear or billion year. A topologically flat, that is a universe which has its density equal to the critical density, in that case its age will be 13.6 gigayears. So this is a very interesting issue, to know the exact value of the Hubble parameter H naught. And later, see, the attempt is continuing in 1974 and in another attempt in 1982. These same astronomers got values of H naught between 50 and 57. And in 78 and 86, another astronomer made the measurement, and he obtained the value H naught between 90 and 110 km per second per megaparsec. So that second value, 90 to 110, is again threatening of an age problem once again. So this continues, this issue continues. I just want you to introduce some of these techniques where H0 is measured over the years. There is a so-called Tully-Fisher method of measuring H0. And in 1977, that technique gives a value, gave a value 75 to 80 kilometer per second. That still is a higher value, a larger value, which that may give rise to some age problem. So the value of H0 and its close relation to age of the universe, that is the issue here. So this is another technique of this picture shows a gravitational lensing, and this can again be used to estimate the value of H0. And in 1964, this gravitational lenses were observed. A value of H0 was estimated. The value of H0 in that case was 50 to 75 kilometer per second per megaparsec. And later in 1990, the Hubble Space Telescope, you all know this, a telescope which is orbiting our Earth, the Hubble Space Telescope. It was launched in 1990, and several attempts were made to measure H0 using the data, especially the Cepheid variable stars data from HST. And these people obtained a value of H0 equal to 58 plus or minus 6, 58 plus or minus 6 kilometer per second per megaparsec. Actually, that itself contains some 10% error. See, the importance of H0 is that in almost all calculations in cosmology, you will need this parameter. So we have to understand this error, such large error in the value of H0, which indicates a certain inaccuracy in all calculations in cosmology. So the Hubble Space Telescope was used by several astronomers. This is Wendy Friedman in 1994. She obtained a value of 72 plus or minus 8 kilometer per second per megaparsec. 72 plus or minus 8. That again had this problem of raising the problem of age, the discrepancy between the age suggested by this value of H0 and the actual age of the universe, as we obtained from other measurements. So the supernova in 1998, you might have heard of the supernova observations, which led to the concept of accelerated expansion of the universe. How it comes, there is an acceleration that is actually inferred from the supernova data. Supernova data are binary star systems, and they are said to be standard candles because supernovae can be effectively used in very efficient way to estimate distances. Actually, these galaxies are so far away from us, and it is quite difficult to make the distance measurements. And these people made accurate measurement of distances to these supernovae, and they came to the conclusion that our universe is now expanding in an accelerated manner. So far it was considered to be decelerating. But now people think, or these observations in 98 led to the concept of an accelerated expansion of the universe. Actually, this data cannot be directly used to estimate the value of H0. So I just mentioned when there is the accelerated expansion declared, people consider the present universe to be dominated by dark energy. I hope you have heard of terms like dark energy and dark matter. Dark energy is sometimes, theoretically, it is considered to be arising from a term, the cosmological constant, which has a negative pressure. That may be causing the accelerated expansion. But this observation has the positive effect that it relieves cosmologists from the age problem. Even though the value of H0 is high, more than 70, Perhaps they thought that the supernova observations will relieve cosmology from the age problem. This model of the universe, which contains ordinary matter, dark matter and the dark energy, is sometimes called the lambda CDM model. Yesterday Suresh mentioned this lambda CDM model and details of that. I just want to tell you this just one thing. If there is a lambda CDM model which contains only 5% visible matter, actually the observable visible matter in the universe is only 5% as per this lambda CDM model. The remaining 25% is dark matter, and the 70% of it is some unknown, very mysterious dark energy. See, actually all this points to the need of measuring distances accurately. Various distances. Actually, when there is an object like moon or sun or some other star in our own galaxy, one can use the method of parallax to measure distances. But when you go to further and further distance, you have to devise newer and newer techniques. So such a thing is usually referred to as a cosmic distance ladder. Various techniques are devised to measure distances. Actually, for us to believe what is being said by cosmologists, that should be based on accurate data. See, the measurement of distance is a very important aspect in cosmology. So this is just an outline of what this cosmic distance ladder means. Now, you all might have heard of this cosmic microwave background. See, the universe, when we observe with telescopes, there is a maximum distance to which we can observe using ordinary telescopes, except the gravitational wave detector we have started to use recently. All other telescopes can observe the universe up to a maximum distance, and that maximum is that maximum distance we have a surface which we call the last scattering surface, and the scientific name is the cosmic microwave background. So this is a picture of that microwave background. And the CMB observations are a very important part of cosmological observations recently. These are various techniques of using balloon experiments. In the earlier times, the CMB was observed using balloon experiments like boomerang, and then there is the Kobe satellite. In 1989, a satellite was launched to measure or observe the cosmic microwave background. And there is a technique of measuring H0. I mentioned CMB in this context. There is a technique of measuring distance using the CMB. That is based on the dimming of CMB, and the famous astronomer Seldovich. He measured this value in 90 to 95, in the period 90 to 95, to obtain a value of H0 between 40 to 70 kilometers per second per megasecond. See, actually till now there is no consensus on the value of H0. That is the main point I want to bring to your notice. Even now we are not able to see. In 2001 there is another satellite launched which is called the WMAP, that is the Cosmic Background Explorer satellite, in 2001, and that satellite was also used to obtain very accurate pictures of the cosmic microwave background. So these are two pictures. The first image is that observed by Kobe, and the second is what we obtained from the WMAP satellite. And lately, in 2009, a more accurate measurement is made using the Planck satellite. That operational since 2009 to 2013. And this power spectrum of the temperature fluctuations, that is a very important set of data we obtained from CMB, the power spectrum, and the power spectrum can be used to estimate the value of H naught. And the value of H naught we obtained from this Planck data, and that is a model dependent calculation. That means the lambda CDM model which I mentioned earlier can be used to estimate the value of H naught based on this data. The value obtained is 67.4 plus or minus 0.5 kilometer per second per megaparsec. So this value is claimed to be very accurate because the error bar is only 0.5. When compared to its value 67.4, the error bar is very small, and all the cosmologists who work in the lambda CDM model claim that this value should be precise. So if the lambda CDM model is correct, then the present value of Hubble parameter should be 67.4 plus or minus 0.5. So this is the origin of the problem, the Hubble tension. I want to mention the Hubble tension. So the Planck's satellite or the Planck data is used to estimate the value of H naught to be such a low value when compared to the value obtained from, see, this is regarding the another technique called baryon acoustic oscillations. There also we get the value of H naught to be 67, the same value with almost 1% accuracy. That is early universe. See, this COBE, this cosmic CMB and other techniques are used to estimate the value of H naught based on data from the early universe. But Adam Rees, I just showed his picture earlier. He was one among the people who observed discovered the accelerated expansion of the universe, and they were awarded Nobel Prize in 2011. They were awarded Nobel Prize, and Adam Rees even now is very active in cosmology and is making measurement of H naught, and his value is still it is very interesting. He obtains a value 73.3 plus or minus 1. Say a Nobel laureate like Adam Rees obtains a value of 73 plus or minus 1 kilometer per second units. So this is in sharp distinction with the value predicted by CMB, lambda CDM model using CMB. Okay, that value was 67 plus or minus 0.5, and the value obtained by Adam Rees and his collaborators is 73 plus or minus 1 kilometer per second. So they are vastly different. The difference is said to be almost 5 sigma. In statistical terms, we say the difference is almost 5 sigma. So there is a very serious discrepancy in the value of in the measurement of the value of H naught. Again, there is another technique called using the tip of the red giant branch, TRGB. The Wendy Friedman, I showed this astronomer earlier. Wendy Friedman is trying to measure the value of H naught based on TRGB, and what she obtains is some 69.6 plus or minus 1.7. So this value is somewhere in between those two, 67 and 73. Okay. So this gives a summary of observations made by all these people. See, this gray picture is what predicted by CMB, and this blue one is what predicted by Cepheids as measured by Adam Rees and collaborators. So when a physical quantity, actually the expansion rate of the universe is signified by this H naught. That is a physical quantity of very most importance in our understanding of the universe. But the value of H naught is having so much difference. That value is having so much difference. See, this curve is what predicted by the lambda CDM model, whereas this is what obtained by these people from, that is the local measurement. When you use the supernovae data, we are using data with the lower redshifts. Lower redshift means the recent universe. Okay, so such local measurements give a value of H naught somewhere around 73, but this is 67. So such a difference cannot be accounted. Actually, that remains a puzzle, and people are still following it. In 2020, there was a measurement of H naught, and that gave a value 76 plus or minus 5. And there is another technique called the brightness fluctuation techniques of Cepheid variables, and that gives a value 73.3 plus or minus 2.4. So the takeaway point I want to bring is this. Okay. Lastly, we have to mention the recent launching of the James Webb Space Telescope. Thus, James Webb Space Telescope was also used to obtain values of H naught. The team by Wendy Friedman got a value of 69.85 km per second per megaparsec. And using Cepheid variables, they got the value 72.04 units. So, Wendy Friedman's value is somewhere in between what predicted by CMB and what obtained by the local measurements. So this is a very recent measurement by Adam Rees and collaborators. They still stick to their value of 73. So Adam Rees recently said that with the measurement arrays neglected, what remains is the real and exciting possibility that we have misunderstood the universe. See, these are the words of a Nobel laureate who is very disappointed with this disagreement between theoretical prediction and the actual data. So cosmologists are anxiously waiting to see if the tension is relieved by refined data. Lastly, a very recent paper in 2024, that was another technique used called the gravitationally lensed supernova, using the obtained from the JWST, James Webb Space Telescope data. This astronomer Brenda Fry obtained a value of H naught equal to 75.4 km per second per megaparsec. And that again confirms the Hubble tension. So this was the latest result we got from this context of measuring H naught. So all this confirm to the point that at present cosmology is in a disarray. That is, we are not sure about, there is almost 5 sigma uncertainty in the value of H naught. And H naught is, I told you, the most important value in cosmology, because in almost all theoretical calculations, you would need this value of H naught. But such a constant is still having a very ambiguous, its value is quite uncertain even now. And that is what we refer to as the Hubble tension. So those who are working in the field of cosmology are still working very hard to resolve this puzzle. And even though we have mentioned this Hubble tension several times in theoretical models, when people present theoretical models, they always mention the term Hubble tension. This is a background of that term. I just wanted to give an overview of such a hot topic which is still discussed in cosmology very recently, and it is a very important recent development in cosmology. So thank you all for your patience.